Hello, and welcome to this presentation on statistically enhanced decline analysis by Boyd Russell. This presentation was given at the NAPE Summit in February of 2016.
What's a reasonable forecast for one well? What's a reasonable forecast if you're going to be aggregating 10 wells? Is the range of probable outcomes different? It is. How do you quantify this quality? And to honor reserve definitions, and I'm talking about the definitions that we find in PRMS in most of the world and COGI in Canada. Those are specific definitions. How do you honor them, both for single wells and for aggregation? And part of that is that the quantities you actually recover meet or exceed what you say they're going to be. For instance, proven in COGI is P90, or 9 times out of 10 you're going to get more. PRMS, highly likely you're going to get more. How do you guarantee that? And remove bias. Because you have 10 engineers in a room, they'll come up with 10 different answers. And get better 1P and 3P numbers. What's the problem? First off, the problem is that your best fit, your best estimate, if you're using deterministic, isn't necessarily P50, especially in unconventional wells when you're still in a linear flow and you haven't seen a boundary. It isn't giving you a P50, and there's no method out there that'll give you a P10 to P90. So what do? Take the P50, we try to tweak it, fit a pessimistic trend. I can guarantee you there isn't a P90 trend built into wells. These are probabilistic expressions. They're not deterministic. And production is deterministic. It is actual numbers. We'll adjust terminal declines. We'll use analogs. Specify ratios. Okay, I had a big reserve house that said, okay, we do our best fit and then we take 70%. And that's our P90. Well, maybe 70% might be good if you've got about a year and a half of history. Is 70% good when you have 5 years? Absolutely not. So, what is that number? We just guess. And I referred to inferred aggregation. Aggregation's not included. So really, decline analysis does not satisfy reserve definitions, nor does it take the benefits of aggregation. The basic premise of SEDA is threefold. A best fit forecast, if you adjust it for bias, will be a 2P reserve. The next one is a best fit forecast is dynamic. It changes with time. Your best fit forecast, if you have a year of history, it's really different than the best fit forecast you're going to have 3 years, or the best fit after you've seen boundary dominated flow. It changes. And for a specific period of time, there will be a constant ratio between the remaining reserve categories. And I'll elaborate on that a little bit more in a second. And in developing this was the game plan. We needed analog wells, or we needed wells with sufficient production history. And we then took these wells. These were Barnett's. These wells all had 12, 13, 14 years of history. So what we really ended up doing is taking these wells with 13, 14 years of history, forecasted them all. A lot of them, or if not all of them, were in boundary dominated flow. So we got really accurate forecasts. Now we took those same wells and we truncated and said, okay, what if you have 6 months of history? What answer would you get? If you had a year, 18 months, 2 years, 3 years, and we determine ratios between truncated forecasts that are real answer for large numbers of wells. And then we use Monte Carlo, and we said, okay, if it's not just one well but many wells, what is the range of your, let's say, P10 to P90, your distribution, if you have a large number of wells. And what we're going to do is we'll show how this all comes together. Okay, we forecasted 550, and they really were random wells. Interestingly enough, the quality of forecast was excellent for all of the ranges. When I say 6 months to 8 years, these are wells that it's the same well. What if you have 6 months? What if you only use a year of data? So we did backcasting kind of exercises. Our range of answers was really from -4 to +5%, which is really quite incredible for ultimate recovery. You'd be happy if you get that. The 6 months in a 1 year forecast, they were here. They were within, like, one was less than 2% and one was like 5%. 6 months of data, I was able to get that close to if I had 12 years. Pretty amazing. But we use something called analog forecasting. I can talk about that a little bit in a minute. What do I mean by remaining reserve ratio? What we took is the EUR at a specific time. What's the EUR I get if I have 6 months of data or a year of data, minus the recovery to date versus the EUR I have with all the data versus the recovery at time. And I build this ratio. So for 6 months, I had 550 ratios. A year I had 550, and so on. Okay? Now, what I'm doing here is I'm plotting these answers from 6 months to 8 years. And as we expect, it is getting steeper with more history. But what's interesting, see the black? That's 6 months and a year. 6 months and a year data is probably my best data. And it's the least history. And I'm using, you guys know what analog forecasting is? What I did is I built type wells for wells with 5 years of history. I used those type wells, and I superimposed automatically, did that automatically. I imposed those type wells and aligned them with the production, or at the right cume, for all of the wells with 6 months and a year, and I used that as my forecast. And we use this method all the time with wells with not much history, and the forecasts are amazing. So this is the ratios. Another interesting thing, it doesn't, with a ratio of 1, doesn't go through P50, which is kind of an interesting, it doesn't have to. Okay. So here's the application. At P50, we have a reserve ratio of 1.05. At P10 is 5 and 0.38. So it's a fairly high. It's this is, I believe, is for 2 years of data. It's a fairly high reserve ratio. We wouldn't be using this, and you'll see in a minute why. Now, we took this same ratio and we aggregated it for 10 wells. How did we aggregate for 10 wells? Is that we took, of the 550 wells, we took 10 random wells, determined a ratio. Took another 10 random wells, determined a ratio. Did that, I believe, did I say here, about 100,000 times. Got very steep, still did not go through the P50. So the benefit of 10 wells clearly reduces your P10, your high side, and also reduces your P90, your low side. So when I said the aggregation for 10 wells, we had done this, I think it's 500,000 times or 1 million times. We did this for 1 well, 2 wells, 10 wells, 15, 20, all the way to 1,000 wells. So now what we're plotting is a trumpet plot. So, and when I say P90, I mean 9 times out of 10, the number was greater than or the ratio was greater than this. And only one time out of 10, the ratio was higher than this. And this is for a well count of 1 to 1,000. So consequently, if you want to, you do a forecast for a well. If you want to say, what would my realistic P90 or P10 be, it gives you a factor that you can use. Here's the application of this. Here's a well. This is the best fit. The adjustment for P50, P90, and P10. And how I did it here is all I did is I adjusted the terminal decline. I've also done it by adjusting the D, the B, to get effectively the same answer for P90. So now I can say, depending on the number, I should go back. 1 second. I failed to mention something. Whoops. But what I'm showing here, this is using 5 years of data. I've done one of these for 6 months, 1 year, 2 years, 3 years, 4 years, 5 years, 6, 7, 8. So I can get whatever aggregation I want, and also whatever year of history I have for that particular well. If it's a 3-year well, this will be a different plot. And if I have something that's between 3 and 4 years, I'll do an interpolation between the 3 and 4 year plots. And does it work? Well, I applied this. I did it on I developed these set of type curves with 550 wells. I kept 350 wells aside. Then I compared the 350 wells. I took random samples and I looked at the answers. So I did 10,000 samples. I said, okay, in this sample, how often is it above the 90% or whatever? And in all cases, the answer that I was predicting using SEDA was duplicated with the actual well. So I proved independently that this method, in fact, gives you 9 times out of 10 you're going to get more if you're aggregating whatever you aggregate, or 1 time in 10 you're going to get more. So basically, I confirm that we can use this method to generate realistic, probabilistic forecasts off a decline, off decline analysis. So it resolves the deficiency with deterministic forecast, because that's a 1 number. It improves your certainty and accuracy. It definitely increases your 1P and likely your 2P reserves. And we believe that this is reliable technology. It's yet to be proven. We've done a number of backcasting and auditing studies with this. There is a paper on this that covers it in a whole lot more detail. It's yet to be shown if it's going to be reliable technology, but we believe that the science is sound and the math is sound.